Hello, everyone, and welcome to today's webcast, Industrial Water Reuse and Recycle, Where to Start, sponsored by Evoko Water Technologies. My name is Angela Godwin. I'm Chief Editor of Water World and Industrial Water World magazines, and I will be your moderator today. A few quick housekeeping items before we begin. The slides for today's presentations will be pushed out to your screen automatically. A PDF of those slides is available in the Event Resources tab in the console window. This presentation is both live and interactive, so that means you can ask questions at any time by clicking on the Ask a Question button in your presentation window. If you're running any pop-up blocking software, you will need to disable it to view this webcast. In addition, it is recommended that you close down all other applications for better performance. If you should have any technical difficulties during the webcast, please type your issue into the Ask a Question box and a member of our webcast support team will work with you to correct the problem. A certificate of attendance will be issued automatically via email to all attendees at the conclusion of the presentation. Just please be sure to stay logged into the webcast until you see the congratulations message. That's a cue for our system that you want your certificate. For your convenience, the presentation will be available on demand within 24 hours of the live event. A reminder email message will be sent out to all registrants with a link to that archive. It will also be accessible from our homepage at waterworld.com. We have two terrific presenters for you today. Scott Barham is the business manager for the power market vertical at Evoko Water Technologies. He has more than 25 years of water treatment experience with positions in business development, product management, and applications engineering, and previous employment with Siemens, US Filter, Polymetrics, and Dicep Systems. Scott holds a BS in engineering physics from Oregon State University. We also have Hari Gupta. He's Director of Applications Engineering for Heavy Industry at Evoko Water Technologies. He has 44 years, 40 of those with Evoko, of water and wastewater treatment experience, including process design, system configuration and design, cost estimation with focus on lifecycle costs, and service offerings such as mobile and land-based systems. Hari holds an MS in Chemical Engineering from University of California at Berkeley. And now, without further ado, I will turn the program over to Scott.
Great. Thank you, Angela. Hello, everyone. Today we're going to discuss water reuse and recycle. We'll touch on 5 specific areas for consideration. I'll discuss the first 2 topics, and Hari will discuss the next 3. These topics include recycle reuse water drivers, guidelines that shape and impact those drivers, opportunities within your plants to reuse and recycle your water and wastewater, solutions to achieve reuse and recycle goals, and finally we'll look at a couple example projects. At the end, we'll have an opportunity for questions. As we go through this presentation, there are a couple of survey questions we encourage you all to participate in. And let's start out with the first question. Angela?
Sure. Thank you, Scott. So we'd like to ask our audience, what is the number one reason why you would recycle and reuse water in your plant? If you would select a choice there, you have freshwater and sewer water discharge costs, sustainability goals, community relations, pressure, regulatory pressure, plant water treatment limitations, or limited supply of fresh water. We'll give you guys a moment to answer that, and then Scott, I'll hand it back to you to discuss the results.
Great.
Super. I see the results coming up now, Scott, on that surveys tab. Starting to come in. I'll give you guys just another minute here. Excellent. Looks like quite a variety. Scott, are you able to see the results?
Yes, I can see them. So it does look like the primary issue is sustainability goals, which is great. We'll talk about that a little bit more here in a minute, as well as the limited supply of fresh water. And I think third or close to that is the freshwater and sewer water discharge costs. So great. So what are some water recycle and reuse drivers? As you can see, they include water and wastewater discharge costs, water scarcity, regulatory challenges, sustainability, social pressures, and a plant's limitation to process existing or future wastewater needs. So let me get into this. This slide represents the impact of water costs over time, whether it's the cost of feed water or wastewater. It may surprise many of you that the water cost challenges are not isolated to drought-restricted areas or high-density populations. These examples are for the state of Ohio, but the issue is similar in many regions of the country. The graph on the left depicts the cost of treated water over time, and the graph on the right depicts the cost of sending wastewater sewage over time. As the data in the graph show, water rates increased on average 4% per year above inflation, which is represented by the red curve over the 14-year period. Cost of water is an issue we need to monitor and stay ahead of. Water availability or scarcity, of course, is a driver. Drought impact can be both seasonal and long-term. Not only may it be more difficult or costly to obtain water, but the water quality can change as well. Oftentimes in a drought, the source water conductivity rises, increasing existing treatment costs. And you may not have access to a pre-treated source, such as municipally treated water. If your only source is a well, you may have issues with the elevated total dissolved solids, iron, manganese, hydrogen sulfide, or other contaminants. If your source is surface water, it may be high in total solids or suspended solids or organics. Urban population growth also puts a strain on the availability to obtain water and on the infrastructure that delivers fresh water or receives water. These factors can lead to water rationing, as we recently witnessed here in California, where I'm at, and that can be important, and that can impact your ability to produce your product. This slide shows the changes that can occur over time specific to drought. The map on the left is how we looked in May of 2015. Everyone is surely aware of the struggles that occurred in the West and in Texas. You can see that in the dark red areas identified on the map. The map on the right is how we look today. So while the drought has abated here in California, Florida is now beginning to feel the impact. Regulatory challenges may also drive water reuse and recycle strategies. The limits defined in your existing discharge permits may hinder your growth. You may be restricted by daily volume, water quality, or other issues. Treating and recovering a portion of existing wastewater may be a great way to allow production increase without violating permit volume restrictions. Ari will describe an example of this later in the presentation. And of course, guidelines change over time, such as recent changes implemented specific to the effluent limitation guidelines and the coal combustion residuals regulations to the power industry. In these instances, power plants are now having to address existing discharge protocol, having to add treatment processes, or even shutter their plants. So I don't typically read a slide verbatim, but I think this one's important. This definition of sustainability comes from the US EPA, and sustainability was one of the higher rated questions at the beginning of our poll. Sustainable manufacturing is the creation of manufactured products through economically sound processes that minimize negative environmental impacts while conserving energy and natural resources. Sustainable manufacturing also enhances employee, community, and product safety. So what does sustainability mean to you? To me, as I see it, it's an increase in operational efficiency, reduced costs and reduced waste, improved production capacity, and strengthening of your brand and your reputation. Sustainability is important. While our own political environment may be in a state of flux, globally, protecting our resources is a valid concern. Negative publicity can and does hurt a company's sales and growth. And watchdogs are not just organizations anymore, but common citizens who can report violators and get results. This is driving corporate social responsibility where companies are searching for positives. I think the blue box is important. In the past, news only related to water pollution caused by corporations. But today, with greater focus on water conservation, that stigma is changing, and that's a good thing. So one area that may handcuff growth is the limitation of a plant's existing wastewater treatment plant. When originally installed, it was designed for a specific purpose, surely. Often that purpose changes over time. This sensitive, fidgety equipment may now be taxed with handling greater flows, higher concentrations of waste, etc. Struggles will occur. And while one can certainly invest in upgrading and adding equipment to treat more and more flow, another approach could be to reduce a portion of the wastewater and recycle it to other plant processes. Excuse me one sec. So how do you start to reuse and recycle your wastewater? We see this as a three-step process. First, evaluate your existing processes, where you use water today and where you might reuse wastewater, if you could clean it. Gather good data. Second, set some obtainable goals. Do you need to further treat it? Should you include future expansion as a consideration? Of course, to do this, we recommend you work with a reputable water treatment company to develop and execute your plan. And finally, act upon your decisions. So let's mention a few potential hurdles and challenges. Some hurdles you might encounter may be logistical in nature. You may not be able to move water from one point to another within your plant. You may not have adequate space to add equipment to reach your goals, and it may seem to be a challenging financial decision to implement. Other hurdles you may encounter might be regulatory or personnel-based in nature. The waters may be very challenging to further treat. Qualified labor to maintain new equipment might be challenging and costly to source. Of course, outsourcing of operation and maintenance with a reputable water treatment company might be an option. Great. At this point, I'd like to turn it over to Hari to discuss opportunities that exist and offer some examples of the benefits of recycle recovery implementation. Hari?
Thank you, Scott, and hello, everyone. When examining areas where you can recycle water, some areas are more simple than others. Generally, a good place to start is to look for the low-hanging fruit. Stormwater recycle can be fairly easy with little treatment, depending on how you want to use the water. Many people ignore this water for recycle because it is variable in quantity and quality, but it can be a good source of low-cost water for your plant. Some other sources of water that may be easier to recycle include softener and DI rinse waters, process tank rinses, waters used for testing of products, and backwash wastewaters from your water treatment plant. The Alliance for Water Efficiency ran a study a few years ago and found that among 5 plants investigated, a combined total of 66 million gallons of water could be saved every year fairly easily, with a very short payback period. It shows that low-hanging fruit should not be ignored. Some water sources at your plant can be relatively more difficult to recycle depending upon the treatment required for reuse. But do not ignore these streams when developing a plant recycling plan. Plant wastewaters, boiler and cooling tower blowdowns, and RO reject are some sources to examine because these streams are often continuous. These streams can vary in composition, therefore the treatment of these waters can be complex and will depend upon where the water can be reused. An additional source of water for the plant can be secondary or tertiary treated municipal wastewater or gray water. Treatment and reuse of these waters has been in practice for several years. In addition, a total plant water balance with stream composition should be developed for each plant if one doesn't already exist to provide an overview of water usage and wastewater discharge. The economical analysis should include the cost to treat the water streams for reuse versus the current cost of fresh water and wastewater discharge. Before we move on, we have another survey question. Angela?
Yes, Hari, thank you very much. So you will see a survey question pushed out to you, and we'd love your feedback on this. And the question is, what areas in your plant could provide the simplest sources of reliable water for reuse? Your choices are cooling tower blowdown, wastewater discharge, boiler blowdown, once-through flows, washdown or rinse waters, and reverse osmosis brine recovery. So if you would all just take a moment and make a selection. Excellent. I see results are starting to come through. Hari, are you able to see those results?
Yes, I do.
Excellent. I'll hand it back to you then.
Thank you. So here are the results. The category B, which is a wastewater discharge, is the highest in terms of the holding, which can be considered for reuse and recycle and reuse. The others are E and F, the wash down rinses, which are again a low-hanging fruit, and the reverse osmosis brine recovery, which is in most of the plants, and it's a really good source of water. This slide shows a snapshot of many Evoko water technologies and products that are often used for developing water recycling solutions. Some of these technologies and products are a great fit for challenging waters, while others can be used effectively to treat relatively clean waters. These systems can be used alone or in combination, depending on your treated water quality requirements. The solution development phase will need to optimize the treatment scheme to provide expected rate of return on investment. We do not have time to go into the details of these technologies and products, but I do encourage you to go to the Evoko website, www.evoko.com. Before we move on and talk about recycling project examples, I would like to highlight two solutions that are very commonly used in water recycling projects: media filters and reverse osmosis systems. These solutions, such as Evoko Vantage reverse osmosis units and Vortisand filters, are proven and reliable technologies that can be used individually or as part of a system, depending upon your water quality requirements. The first recycling example is at a chemical plant in western USA. This plant uses high-pressure steam in their process. High-quality boiler feed water for steam production is produced using media filtration, ion exchange softening, reverse osmosis, and ion exchange DI polishing. Feed water to the system is supplied from a local municipal source. Plant management approached Evoko for developing a solution to reduce the use of municipal water without affecting the overall treated water flow. This was based on both the limited availability and the increasing cost of municipal water supply. Evoko's solution included the installation of a RO reject recovery system, which will treat the RO reject stream from the primary RO system. The permeate from this RO reject recovery system is recycled to the front end of the primary RO system, thereby proportionately reducing the flow rate of incoming municipal feed water. This solution also provided about 50% reduction of the primary RO reject flow to their wastewater plant. In this system, Evoko also incorporated remote monitoring of system operation to provide timely information about water qualities and flow rates. Here is a block diagram of the recycle solution incorporating the RO reject recovery system. The plant was already comfortable with reverse osmosis technology as part of their primary system. Additionally, there was plenty of room for the new equipment installation. The addition of this RO reject recovery system is saving about 200,000 gallons of municipal water per day, plus proportionately reducing the wastewater discharge volume. This solution is providing a combined savings of about $25,000 per month. Both are very significant numbers. Besides the water savings, this project was good for the community because this area is often challenged with insufficient water supplies. The second example of the recycle project involves reverse osmosis, but it has different configuration than the earlier example. In this case, the plant's primary system also produces high-quality RO water for process use and steam production. The system consists of media filtration, ion exchange softening, and reverse osmosis. Feed water is clarified river water. Plant management approached Evoko for a solution to provide more treated water flow without increasing the size of the primary system. This was accomplished in phases. Initial, or the first phase, was the installation of the original water treatment system to produce 1600 GPM RO water. Second phase included the installation of an RO reject recovery system to reduce the influent clarified river water, similar to the earlier example. The third phase included the addition of another reverse osmosis system as a second pass to the RO reject recovery system. Instead of recycling the RO rejects permeate to reduce influent river water, the second pass RO is further treating this permeate to a quality similar or better to the primary system permeate. Both streams are blended to provide more total water flow with the same volume of influent clarified river water. The overall water recovery increased from 75% to greater than 85%. This illustrates that the recycle plan can be implemented in stages or can be all done at once. Here is a block diagram of the combined system before and after the recycle solution. You can see that the permeate from the two-pass reject recovery system is blended with the permeate of the primary RO system to provide an additional 220 GPM of treated water flow without increasing the flow of the clarified river water to the plant. Additionally, there is some improvement in the overall treated water quality as the two-pass permeate is better than the primary system permeate. The third example of the recycle project incorporates the use of municipal gray water as a water source to supplement existing sources. Gray water is treated municipal wastewater, treatment typically consisting of biological process, secondary clarification, and media filtration. Billions of gallons of municipal gray water is currently discharged to waterways around the country and internationally. The gray water is treated by the municipality to meet local NPDES permit requirements. The composition and quality varies seasonally and from site to site. This wastewater is good alternate source of water supply for industrial reuse. Treatment technologies are well established and have been in use for several years. Plant management approached Evoko to develop and operate a pilot system using municipal gray water as a feed source before the full-scale system can be implemented. Bench scale and field pilot programs are useful to develop and verify the efficacy of the treatment scheme. Gray water composition varies seasonally and from site to site. A detailed analytical data on gray water and the quality required for treated water are important parameters to develop and optimize the treatment scheme. Clarified river water is the primary source for the existing water treatment system at the site. Gray water available at the site has higher conductivity, nitrates, and organic levels compared to the river water. This treatment scheme consisted of 3 unit operations: coagulation, ultrafiltration, and two-pass reverse osmosis. Treated water is used for process and boiler feed makeup. Membrane pretreatment is very common in treating gray waters, especially as the feed to the reverse osmosis units. This process was piloted successfully and recommended for the full-scale system. Gray waters for industrial use are becoming common and cost-effective solution for sustainable source of water supply. So to summarize, recycling and reusing your plant's wastewaters can reduce your costs as well as the load on your wastewater treatment plant. It can provide additional flow to changing production needs at your plant, and it can improve your plant's impression to the surrounding community. As Scott mentioned earlier, when you are ready to start a recycle and reuse program, remember to evaluate your current conditions, set achievable goals, and then execute. As we discussed, some of these projects are simple, some are more complex. Be sure to work with a good water treatment company and utilize their expertise. That's all of the slides we have today, but before we move on to Q&A, I believe we have one more survey question. Angela?
That's correct. Yes, Hari, thank you. Yes, before we move into the question and answer portion, just want to poll our audience one last time to understand what time frame you might be considering starting a water recycle project. If you would just take a moment to make one of the selections, the options are immediately, in 3 to 6 months, 6 to 12 months, or longer than 12 months. And then finally, not planning on recycling water. Your feedback would be very helpful. So if you just take a moment and make one of those selections, we would appreciate that. And while you do that, we actually can go ahead and move into the Q&A. I do want to let folks know in advance that if you have not had a chance to enter into a question, you can still do that. You just click on the Ask a Question box, and you can enter in your question. And I want to let you know, too, that any unanswered questions will be forwarded to the presenters so that they may be able to answer those offline. So let's see, with that, let me just jump right in to some of the questions that have come in already. How would you recycle cooling tower blowdown? What could you use that water for?
Scott, you want me to take that?
Yeah, Hari, go ahead and take that one.
Okay. The cooling tower blowdown reuse involves several steps. The steps we should go through is a review of the cooling tower design and operating parameters. We should look at the makeup water quality, the chemical treatment program for scale control, biological control, cooling tower blowdown analytical data. We should look at the historical data of the cooling tower blowdown at least over a 12-month period to be able to provide good design parameters for the system. Typical impurities in a cooling tower will include TSS or turbidity, cycle depth concentrations of the makeup water, which could be total hardness, alkalinity, conductivity, pH. It will include some metals and organics. The treatment schemes typically, like we mentioned before, is a function of the reuse of the water. For TSS turbidity reduction, typically it will be a clarification and filtration, and even now the ultrafiltration. For scale control, it could be a physical chemical precipitation process, depending on the level of scale control which need to be done, or a conventional treatment. For TDS reduction, that's total dissolved solids reduction, this will be based on the intended use of water. It could be reverse osmosis, single pass or two pass, or ion exchange resins.
Okay, terrific, Hari. Thank you very much. Let's move on to another question that came in. Can Vortisand be used following standard activated sludge clarification as RO pre-treatment? Namely, can I get RO permeate from a biological treatment plant without having to use MBR?
Scott, you want me to take that?
Yeah, go ahead and take that one too. Thank you.
Yeah. The Vortisand filtration is a single media filtration system. It has a jet mechanism to keep the top level of the suspended solids so they can be easily backwashed out of the system. For a biological wastewater to be filtered through it, we will need to examine the composition, look at if any chemicals are being used which may impact the performance of the Vortisand filters. And there are other filtration systems, which are available, multimedia, dual media filtration, depending on the quality of the wastewater. And the second question was the RO permeate. I think again that will depend on the composition of the wastewater and the design of the RO system. Certainly after MBR, that water is good enough to feed a membrane to reduce the total dissolved solids.
Terrific. Thank you very much, Hari. The next question for you guys is, are there any government programs that could assist financially when starting a recycle project?
Hari, this is Scott. I'll take that one. There definitely are, and there's a lot of resources online that you can source and find information on that. I'm out in the West. I'm close to Los Angeles area, so in the Los Angeles area, I know that LADWP as well as the Metropolitan Water District they offer incentive programs to drive industry to recycle water, and I think it's definitely something you should look into.
Great, thank you very much. Now, for any of our audience members that have been wondering about cost, is there anything that you gentlemen would tell them or a way that they would be able to find out more details?
Hari, I'll start with that if you've got anything you want to add. It's a life cycle cost evaluation. You're probably going to be adding equipment, which is a cost to you, but the net effect of adding that equipment is that you're probably going to ideally save water and or not need water at other processes, so your feed water volumes potentially would go down, and the amount you'd be paying for that water would go down. And similarly, the waste discharge, instead of discharging, you're recovering it, so anything going to sewer that you might be paying for would also go down. So I think you need to look at it as a kind of a whole holistic view of everything, and then take it over time, and then understand the payback.
Excellent.
Yeah, and I'd like to add that the cost will be a function of the treated water quality required, whether it's a cooling tower makeup or a boiler feed water makeup or process use, and then the quality of the wastewater or the stream we're starting with. For example, if you took the municipal gray water and for cooling tower makeup, typically you would only require clarification or membrane pretreatment and manage the rest of the things through a chemical treatment program. If any TDS reduction need to occur, then reverse osmosis can be incorporated as part of the total treatment scheme. So the cost is going to be based on the number of unit operations involved, but certainly, like Scott mentioned, it will balance the payback period relative to the cost of the source water available, which this will be replacing.
Terrific, thank you. Next question, does Evoko offer treatment equipment and processes to remove specific ionic metals such as arsenic, selenium, and other heavy metals?
Scott, do you want me to take that?
Sure, go ahead.
Yes, Evoko offers, depending on the contaminant level, for arsenic and mercury, we have specialized media which can be used depending on, in addition to what other impurities need to be removed before the metals can be removed. We also have a non-biological process to treat selenium reduction, which is becoming an issue for discharge of some wastewaters. Yes, we do.
Excellent. All right. Next up, a lot of the pushback I get regarding water recycling is associated with quality controls. What recommendations do you have for implementing control assurance mechanisms?
Scott, you want to take that?
Yeah, look, I would say that obviously it is typically more complex equipment when we're recovering these wastewaters, and so thorough service and monitoring protocols are required, probably much more so than the equipment you may have. So it's important that you develop a plan to monitor and maintain that equipment as best you can. Ari, you got anything else to add to that?
Yes, I will add, Scott. I think for a system which is designed and started up, we typically recommend developing SOPs, standard operating procedures, which would include each unit operation and their design specifications and parameters. And as the system is operated, obviously monitoring the operation of the system relative to the SOPs. And with the controls available today, these can be developed as a historical database over time. And as well as the training of the operators is really important and critical as well. As the new system goes through startup and commissioning, getting the new operators or the company which is going to be operating the system engaged during the startup and commissioning is also very useful. And then you get a hands-on experience of the entire system, the parameters which will be monitored and over a period of time.
Terrific. Thank you, guys. Next question. Is there any reliable solution for treating RO brine with high levels of sulfate and other minerals?
Yes, Scott, I'll take that. The composition of the RO reject need to be looked at. In addition to the sulfates, we need to see, is it mostly monovalent cations or is it divalent cations? Many times, if the feed water to the RO unit is softened, we will not see much hardness, so it will be mostly sodium or potassium. And the sodium sulfate is very soluble, but if it is a hardness related to the sulfate ion, calcium sulfate can be precipitated. And Evoko offers a technology which can be used to effectively precipitate calcium sulfate from the RO brines and recycle it back to the front end of the system.
Terrific. Great. Thank you. Next question. What are the salts concentrations of the RO feed and reject of the brine recovery RO?
I'll take this. Again, the composition of the RO reject stream is a direct function of the feed water to the RO system. And let's assume it's 1,000 ppm TDS feeding the primary RO system, and most of the RO systems operate at 75 to 80% recovery. So that is a 4 to 5 concentration of solids. So the RO reject from the primary system will be in the range of 4,000 to 5,000 ppm or micromoles, whichever units we are using. And again, the composition will dictate the additional recovery in the brine recovery system. There are two limitations. One is the osmotic pressure of the dissolved solids. And 4 to 5,000 osmotic pressure is about 30 to 40 psi, which is not that high. The brine recovery system can still be in a brackish design range. We can operate the brackish system up to 500 psi. But if the concentration is higher, the seawater RO can be used as well on the brine recovery system. So the composition will dictate the recovery. And in addition, there are technologies. Evoko offers a technology which can even maximize the RO reject recovery design. It lets some constituents pass through, which helps in the cycling of the solids. So the overall concentrations is strictly a function of what the feed water is.
Okay, great. Thank you very much. Next question. How can you handle RO biofouling in municipal wastewater reuse?
Ari, more in your line of expertise. Go ahead.
I will, yes. The municipal gray water, like we mentioned before, it varies from site to site. It also varies in composition. Membrane pretreatment is one of the most effective ways to pretreat the water for an RO feed. And in the membrane pretreatment, it will reduce some organics load of the water. In addition, and the UF or the MF system can be kept pretty sterile with the periodic maintenance washes. And the rest of the program in the RO system is managed through the bioflushing program. There are bioflush chemicals available. DBNPA is one, which on a periodic treatment, weekly or biweekly, are very effective in minimizing the biofouling in the reverse osmosis system. In addition, the selection of the RO membrane is also critical. There are membranes on the market today which are very effective in minimizing the bio issues while maintaining a larger brine flow on the membrane surface to be able to get those things out of the RO unit.
Terrific. Great. Thank you so much. Next question. I know that in RO, in many cases, only about 50 to 60% clean water and the balance is brine. How is that brine disposed of in most plants?
The couple of comments on this. One is the recovery in the RO system should be closer to 70-75%. Again, it's a function of feed water and the hydraulic design of the RO system. Currently, the RO reject streams in many locations go to the wastewater plant, or they can be directly discharged depending on the composition and the local permitting for that facility to the outfall. That's why, especially for an RO system which is operating at 50-60%, it is an excellent point for recycling and reusing that reject and optimizing the overall process, optimizing the design of the primary system as well as then recovering as much of the RO reject which can be to minimize the flow to the wastewater plant or to the outfall.
Terrific. Right. Thank you so much. Next question. Has Evoko provided a design for gray water reuse as potable water?
Traditionally in North America, or I would say in states, the direct reuse, no matter what the treatment scheme is really not acceptable. I think people do think of it as very different, even though the water quality and the clarity is very good, it's better than some of the locally available drinking waters, but it's just not been in practice. But what has been done, which is in Southern California for the last 35 plus years, Orange County Water District is one of the things which was set up in the late 70s. They're taking 100 million gallons or more now of the municipal gray water and treating it through a membrane pre-treatment, and then injecting it back in the ground water table. Because one of these issues and challenges they had in there is the intrusion of seawater into the water aquifer for Southern California. So the 100 to 200 million gallons of that water now is being treated, is pumped back into the ground. Once you pump it back in the ground and repump the water for drinking, it seems to be acceptable. So it is in wide use, and we currently are involved in that system from the pre-treatment standpoint.
Terrific. Great. Thank you, Hari. The next question, how can we remove sulfates in a cooling tower or boiler system?
Like we make sulfate, we need to look at the composition of the water. If the sulfate has hardness present, so calcium sulfate will be a limiting factor for treatment through a membrane or the RO system. So a physical chemical precipitation for calcium sulfate can be achieved. But if the sulfate is not a scaling type thing, then the pre-treatment of the cooling tower blowdown plus a reverse osmosis system to reduce the TDS. The composition will dictate the treatment scheme.
Great, thank you. The next question is, what are the maximum influent characteristics for reverse osmosis systems regarding COD, nitrogen, phosphorus, etc., and how much what's the removal efficiency approximately?
The reverse osmosis has two. There's a brackish water system which are limited to 5 to 600 psi pressures, and the seawater system now go up to 1200 psi and maybe even higher. The level of the organics, RO is the tightest membrane available. It will remove dissolved or suspended material. So the level of organics is important to keep the RO system operating. So the design of the total system is done as a pre-treatment and then the reverse osmosis. So the objective is to be able to coagulate if any of these organics are coagulatable. So we do the coagulation flocculation, then do the conventional or membrane pre-treatment, and then the reverse osmosis. The typical guidelines for membrane feed is less than 5 ppm TOC. On the phosphates and the other constituents is the function of the scaling tendencies. And calcium phosphate is one of the scaling compounds, but it can be managed through pre-softening the water. It can be managed through antiscalants. So again, looking at the composition of the influent water, providing adequate treatment at each step of the treatment thing. In the pre-treatment, then RO, single pass or two pass, and even including the ion exchange polishing, depending on the final water use.
Awesome. Great. Thank you so much. The next question regarding cooling tower treatment. Would it make sense to pre-treat makeup if it's other than potable water, along with CT side stream filter? Would that reduce the need for blowdown treatment?
Yes, it will. The cooling tower program is developed using the makeup water source, and the makeup could be municipal city water, it could be the river water, or could be a well water or a wastewater. So the constituent which are critical are the hardness, alkalinity, silica, and the overall conductivity. So to keep the tower clean, every tower has a basin which will collect suspended material from around the tower area. So a side stream filtration is effective way to minimize the TSS buildup in the towers, and then the subsequent fouling of the water use further down. And Evoko offers the Vodicent filters have been used effectively in side stream filtration to keep the TSS level to a manageable level. On the other concentrations, each tower is designed for a number of cycles, and that is a function of the makeup water quality and the chemical treatment program. There are once-through cooling towers, which obviously have a lot of blowdown straight back to the water source. Typical tower cycles are from 3 to 10, and the higher the number of cycles, the better the makeup water quality has to be. And that's where I think it does pay. So if you treat the makeup water, which could be just minimal, either pre-treatment or reverse osmosis, and then you can take the cycles up to 8 to 10, which certainly will minimize your chemical treatment program as well as minimize your blowdown flow rates.
Okay, great. Thank you. The next question is about maintenance. How is the maintenance from membranes on water reuse? This viewer says that in their experience, this can be very costly and sometimes unpredictable as far as when to change the membranes. Your thoughts?
Or you want me to take that?
Yeah, go ahead, Scott.
You go.
I'll take it. Yeah, the membrane maintenance program is really a function of the overall system design and the feed water source. So as the feed water source is analyzed, and usually need to look at the historical data, or at least over a 12-month period. And so we need to make sure the pre-treatment is adequate. It's a media filtration or softening or activated carbon or membrane. And then once the RO system is designed for a given condition, say 75% recovery, and you got if the water is not softened before the RO, there's an antiscalant program, and there typically will be a sodium bisulfite feed for the free chlorine elimination, and then maintaining the performance over time. You're trying to run the RO system within a given parameters. And doing the maintenance on a scheduled basis. Typically what will happen in the RO system over time, you will build up the pressure drop, which will be either from organics or from suspended material, which cannot be taken out by the pre-treatment system. And so you set your goals that if the clean system has 20 psi pressure drop, and when it reaches 30 or 40, depending on the given feed water, that you will clean the system. And cleaning can be done in 2 or 3 ways. There's a maintenance cleans which can be done on site, simply by flushing the water, flushing the system every time it shuts down, or an RO permeate flushes to keep the system clean on a periodic basis, or then the third is a chemical clean. And depending on the fouling, if it's organic fouling, it's a high pH clean, and if it's a metals or scale control from a calcium carbonate, it'll be acidic cleanings can be done. In a well-designed, well-operated system, the cleaning frequencies of the RO membranes is anywhere from 4 to 6 months. Some can even go 1 year depending on the water source. Okay,
great. Thank you. next question. In your first couple of examples, could EDR have been used as opposed to RO?
Kari, you want me to give you a break and I'll answer that?
No, go ahead.
Okay. Yeah, EDR technology, I think the biggest fallback in those two examples is it's really not going to necessarily reduce silica. It's very good for high TDS brackish waters and even seawater for TDS reduction. But in these examples, silica would not necessarily be reduced. So in the first example, you'd be taking that concentrated silica from the primary RO, which is 4 or 5x, as Hari's mentioned before, and bringing that back to the front end of the system, and that would cause problems to the RO by increasing the silica to the feed. And in the second example, it's similar in that we're trying to recover that water, and that silica would just continue to pass through, and so you'd be sending high silica water product, which would not be desirable. So in those examples, I don't think EDR, such as the Nexus systems that we offer, would be of any value there. Hopefully that helps.
Great, thank you, Scott. All right, next question. It's two-part. First part is, if we were looking to treat water using the technology you outlined in the presentation, what's the volume of water where the technology becomes beneficial in general? And the second part of that is, can the technology you propose be used in batch processes rather than continuous flow?
Yes, the volume of water. I think that depending on the compositions and the intended use of the water, it can get down to very low flow rates. So maybe we have done system for 10, 20, 30 GPM. There are standard equipment available to that size. So one balance will be looking at what the total volume of water is, and typically we will have a storage if the volume is being collected from multiple sources, and have a storage, and then have a treatment system designed which could operate on a batch basis. Typically, the way this reject recovery system do require a relatively higher maintenance than the primary system. But as the pre-treatment is configured for the primary system, the RO reject is a very clean source of water. The only thing it will have is the cycled up concentration of salts. And batch processes certainly are amenable to the solution as well. It will require some storage on the front and the back end as well. But we are currently doing it at many sites, and it is doable.
Great, thank you very much. Next question, can this process be used for water reuse in fruit and vegetable wash in food plants? Yes, again, if the objective is strictly to remove the suspended material, definitely. I mean, there are technologies, clarification, filtration, can be used to take out it, or even before that, some backwashable strainer to take the gross grit out and then do the clarification filtration. But if the purpose is to remove some solids as well, depending on what type of fruit and vegetables are being cleaned, then the pre-treatment can be combined with the TDS reduction step. Excellent. Great. Thank you. All right. We are getting close to the top of our hour together, and we want to be respectful of the time that you've set aside. But we do have time for just one more question. So let me just ask you, gentlemen, with regard to drought management, how can wastewater reuse affect that?
Scott, I'll start that off. Yeah, I think that in drought management or in drought issues, you may have trouble being able to acquire water. As we saw in Texas in the last couple of years, there was a lot of strain on municipal feed systems to provide water, and a lot of restrictions on people being able to get it. So that's where looking at these wastewater recovery opportunities to minimize the amount of feed water and supply water you need is beneficial. As you can see also in the presentation, sometimes that's not a permanent situation and it changes. But you may need to address it, and you may find that moving forward you have a great way to recover water and save costs as well. And I think the other things you need to look at is just as droughts occur, water quality does change, and that can impact your whole operation of your plant, both for your existing equipment and anything else you put in there. And you really need to evaluate what the changes are, make sure that your system's able to handle the changing conditions of the water. Tara, you got anything else to add?
Yeah, I wanted to add, Scott, that I think one of the first steps should be done is the water balance for the plant and optimizing the current treatment systems at the plant. That will help to see where the waste is and where the water is being used, and then optimizing each of those unit processes to effectively minimizing the waste. And we're currently working with several of our customers to develop those plans. In Texas, like Scott mentioned, there was a guidance that to reduce the incoming flow by 10% within a certain time frame. And certainly municipal gray water is a great source of water to supplement, because that's everywhere, wherever people live. There will be some costs involved to transporting that water from the municipal facility to the plant, but most of the plants are located within a given area. So it is the water balance and the current optimization of the current unit operations is really the key to manage the drought conditions.
Great, thank you guys, both of you. So as I mentioned, we are getting close to the top of the hour, so I think we will wrap up our Q&A session. And I just want to, on behalf of Penwell Corporation, I want to thank our speakers today, Scott Barham and Hari Gupta. You guys did a fantastic job. We appreciate it. And I want to thank our sponsor, too, Evoko Water Technologies. The presentation you saw today was Industrial Water Reuse and Recycle, Where to Start. A download of today's slides is available in the Event Resources tab, or you can access it via the link that you see on your screen in the slide. As a reminder, the presentation you saw today will be archived within 24 hours. It can be accessed from the homepage at waterworld.com. A reminder email message will be sent out to all registrants with a direct link to that archive. And remember to stay on until you see the congratulations message if you would like your certificate of attendance for today. With that, we thank you all for joining us, and we look forward to serving you with future webcasts. This concludes today's presentation.
Okay, guys, we